let us refresh our discussion from last time. Who will remind me what is the wave and what is the difference between pulse and the wave? So let's start from the pulse. What is this? Our medium is a string. We have a string and we provide certain disturbance to this string so it can travel along the string, and that's what we actually call the pulse. What kind of properties of the pulse we can describe? So amplitude is maximum deviation along axis y, like displacement of elements of the string. Probably the width of the pulse, I mean the also duration of which corresponds to duration of this disturbance. Can we apply such property as wavelength to a pulse? No, we cannot, because pulse is a single event, like single disturbance. So in order to provide some wavelength parameter, we need a wave, which is created by periodic disturbance of this medium. Then we, instead of just one disturbance, we create a periodic disturbance. Depends what type of periodic force we attach to the edge of the string. Let's say if we deal with some simple harmonic oscillator, it will create sinusoidal wave traveling along the string. Then we can describe this wave with amplitude, with period, and with wavelength. So what are definitions of wavelength and period? Let's start with wavelength. It's a distance between 2 points. And which points are these?
In similar phase.
Which are in the same phase. Yes, that's correct. So 2 points of this wave which are in the same phase. So it means we can pick up amplitude value and the distance between two amplitude values. That gives us the wavelength. And similar, we can define also period. So if we consider a single element of a string with fixed coordinate and look how it is displaced as a function of time, goes up and down, then the time interval between two moments of time when there will be the same phase for this element, that will be the period of the wave. So if we tell that let's say what is transferred by waves, do we have energy transfer by wave? Yes. Do we have mass transfer by wave? No, because there's these elements of the medium are not moving. Only the disturbance which is created in this medium is moving. So it means we transfer energy, but mass is not transferred. Okay. So what type of waves do we know? Two most important types of waves.
Longitudinal and
Transverse. And what the difference between them? How we define them?
the displacement of the particles.
Okay, yes.
Is perpendicular to the motion or parallel to it.
Or parallel. Okay, so that is definition of two most important types of waves. And also we discussed and mentioned several times last time about last lecture about such terms as waveform and wave functions. So what is the difference between them? So what is waveform? Exactly. So at given moment of time, we have information about y, like displacement of the elements of the medium, as a function of position. So y as a function of x. So wave function then what it is? So it provides us both position and time dependent displacement of the medium when wave is traveling along this medium. So we finished our discussion last time with the derivation of the wave function for a sinusoidal wave traveling along a string. And now let us write it down as a reference for us. So y as a function of x and t is equal to a times sinus uh, k times x minus omega times t plus some phase shift phi. And here we introduce this new parameter k. Remind me, what is this? Wave number and how we define it? Yes, 2 pi divided by lambda. So now, first so we will talk mostly during this lecture about velocity, but first let us discuss what will be velocity and acceleration of element of the string moving up and down along axis y. So we know it doesn't move along axis x, but it moves along axis y. So how we come to this point? If we have this wave function, that's actually not so difficult, because definition of velocity, again, we don't specify it's along axis y, it's clear. Then we deal with the element of the string. So that will be first derivative of displacement over time. However, here we have a function of two independent variables, and we obviously need to specify that we are doing it for some given element of the string. So we consider at x constant. So then when we consider x constant, that is so-called partial derivative of this function over time. And x in this case will be considered as a constant coefficient. So what will be the first derivative? That will be minus omega times a times cosinus kx minus omega t plus phi. So that is the expression for velocity. And as you see, it's also a periodic function. So it changes over time. It's not constant. It depends where this element is in the amplitude. It's the equilibrium condition. So velocity is time dependent. And obviously, if velocity is changing, we will also deal with some acceleration. So acceleration in this case will be first derivative of velocity over time, but again, it's a function of two independent variables. We specify that it's at fixed x, and that will be second partial derivative of displacement over time. And here we will end up with minus omega squared times a times sinus kx minus omega t plus phi. So here we have this pre function, like periodic functions, coefficients, which will stand for maximum velocity minus we don't need it, just be omega times a. So that will be observed at y equals to 0. And also maximum acceleration, that will be omega squared times a, and that will be at y equals plus minus amplitude value of the displacement. So this is information which we can get now about the velocity and acceleration of the elements of the string. However, another, in some cases, that's relevant information. We definitely patients to determine it. However, another key parameter which is interested for us when we deal with waves or pulses traveling along the string, what will be the velocity, like speed of traveling of this wave along the string. So now let us think about this. If we have a string and disturb it, create some pulse which is traveling along the string, we want to consider what parameters of the string, like features, will define this speed of pulse per projection along the string. So any ideas what properties of the string will matter? We're not talking about properties of the disturbance, like of the wave, so it's not like frequency or whatever. We have just one pulse, single disturbance, create single pulse, it's moving along the string, um, and obviously properties of the string will define how fast this pulse will move. So what could it be?
Tensions. Toughness.
Tension. What was?
Toughness.
Well, that kind of related to tension because that will result, if we disturb certain material, depends on the mechanical properties, the way how it responds to this disturbance will define what is the tension inside the string. So tension, that is important parameter. So what you expect? Larger tension will result in higher velocity or lower velocity? Higher velocity, because if we think about second law of motion, then acceleration will be proportional to exerted force. Tension is a force. It's a force which is kind of enclosed in this string. So if larger tension means larger force, we get larger acceleration within given interval of time, get higher velocity. So we naturally assume that velocity of this pulse per projection along the string will be proportional to the tension. Okay, there is one more important parameter which will now serve not like a driving force as tension is, which kind of tries to move this disturbance forward. But there is another parameter which will describe the inertness of this medium for any traveling of the pulse. Yes, so actually density, but when we consider or mass of the element of the string, or density when we are talking about the environment like this medium as in whole, and in particular for the string, since it's kind of one-dimensional object, we are talking about linear density, means like kilos per meter. So that will be a factor which will kind of try to resist any pulse moving along this string. As you may notice in gym, there are fitness is two heavy, very thick strings which you're supposed to shake for a long time. Is quite challenging task, quite exhausting. So somehow they are not very light and thin. Otherwise, it would not be fitness. It would be some circus show. But with when it gets more kilos per meter, then it becomes already quite difficult to create any disturbance in such medium. So our suggestion now, before we go into any derivation, that velocity of a wave or pulse projection in along a string will be, so we don't put equal here so far, we put just proportional. It should be proportional to the tension and reversely proportional to this coefficient mu, let's say, which defines this linear density, kilos per meter. So let us keep this in mind. So our suggestion at the beginning. Now let's try to come closer to this derivation. First, we need a like model system. So we have some system of coordinates x, y, and a pulse. So this system of reference is kind of attached to the string, or so it doesn't move with respect to the string. So in this case, the pulse will move with certain velocity v along this axis x. And we, of course, want to consider some small element delta s of this string. Um, so before we go further, we need to introduce one more system of reference for our convenience later. So that will be x prime and y prime, which will move with respect to this immobile system of reference with the same velocity v as the pulse. So it will just move together with the pulse. Pulse system of reference are moving, so they will move together along axis x. So now let us take a closer look to this string element. So we will, let's draw it here, have it here. We have some horizontal direction, some vertical direction. So here is our string element. Very small, but we just enlarge it to show it in better view. So that will be a segment of a circle with some radius r, and the length of this segment will be defined by this angle theta, well, kind of 2 theta, because we have two angles here. Also, we need to draw here tension vectors on both sides of this string. So now we look at this and we see that there will be some resultant uh, radial force which will be exerted on this string element and pointed towards the center of the circle. So this will originate from like y components of these tension vectors. We will sum them up. So this angle is also theta, and this angle is theta. So Fr will be equal to 2, because we have two tension vectors, times t times sinus theta. And here we, for simplicity, we consider that theta is small. So we did that before. We assume that it's smaller than 10 degrees, and we can substitute sinus theta with just theta. And in this case, it will be, in first approximation, equal to 2 times t times theta. So that's our radial force. And now we recall our moving system of reference. So what it gives us? If we consider this pulse and this element of the string with respect to the mobile system of reference, it will move with certain velocity v, which is velocity equal to the pulse projection along the wave, but in the left direction. So this mobile system of reference is moving to the right together with the pulse. So means that this element, which is stationary with respect to first system of reference, will move with respect to the second with the same velocity but in opposite direction. So now we have some radial force exerted on this segment of the string, some small element, and it should be compensated by some other force, which is the centrifugal force in this case, because we can consider this v as a linear velocity of a small object moving along circular trajectory with the center in this point O and radius, the radius of the circular trajectory r. So in this case, we will have some centrifugal force, which compensates this radial force, and we can write that Fr is equal to 2 times t times theta, and that is equal to mass m times v squared divided by r. So now the question is how we define this mass. Let's assume that we know the linear density, this mu. How do we define the mass of this segment? So the length of the segment is delta s. Delta s is equal, when we have a segment of a circle, we know radius and we know the angle. So how do we get the length of the segment?
Theta radius?
Yes, we have product of radius and angle in radians, not in degrees. So that will be for the length, and mass is defined as mu times delta s. However, here we need to remember that we have not theta but 2 theta. So we should put here also 2. So now we substitute instead of delta s this expression. So this mass of the segment will be 2 times mu times r times theta. So that will be our mass of the segment of the string. And now we substitute it here. So we can write that 2 times t times theta is equal to 2 times mu times r times theta times v squared divided by r. So we cancel out these two, this theta, this r, and we see from here that velocity of this pulse traveling along the string will be square root of tension divided by mu. So we have not so far a wave equation from what we predicted initially. Indeed, is proportional to the tension and inversely proportional to the linear density, but here we, on top of that, have a square root. Keep in mind that here we did not specify any shape of the pulse, so means that pulses with all shapes which are generated, like disturbed in a string, will move with the same velocity. And what is also important to remember here, that we had a specific condition that sinus theta can be replaced with theta, means we have small angle theta. So here we look at this figure, this angle which defines the curvature of the segment should be small. So that means that the ratio between the amplitude of the pulse and length of the string should be quite small. Means we kind of this equation should work for small amplitude disturbance, which is traveling along a string, but regardless of the shape of this disturbance, of this pulse. So now, when we already have pretty much complete information about how our pulses and waves are moving along the string, let us consider what will happen when we have reflection. Like first we consider reflection of waves, and then we will go to reflection and transmittance. So obviously, in order to have some reflection, we need to introduce some abrupt change of the properties of the medium, because if we have uniform medium without any changes in uniform properties in the direction of wave propagation, then nothing will happen and reflection will not be observed. So how we can create such a feature of the abrupt change of properties of the medium? In the case of a string, we can consider something like this. We have some pulse traveling along the string, and then the end of the string is attached uh, to the wall, so it cannot move. So it's fixed in given position. So as this pulse will come closer to the wall, the string will exert some force upwards on the wall because this pulse wants to go up, but the edge is fixed. So according to third law of motion, there will be counterforce exerted from the side of the wall on the string, and that will result in the reflectance of this wave or pulse. However, here we need to highlight that the reflected pulse, well, first of all, it will move in opposite direction in comparison to the incident pulse, but what is important here that the phase will be changed, so it will be so-called inverted pulse, and its phase will change by pi, so 180 degrees. If we have a bit different situation, so let's say we have pulse moving to some like edge with some light ring, which can freely move along a pipe. So a pipe here. Then when this pulse is reaching the edge, this ring will move together with the end of the string upwards without any problems because it's not fixed as was here in previous example. So it goes up and then goes down. In this case, when we also have reflected pulse, but which moves also in opposite direction to the incident um, pulse, but its amplitude will be the same, so it will not be inverted and phase will not change. So that's an example of just reflection of the pulse. Now let us consider what happens when we have interface between two mediums. So actually interface is, you will figure out, I'm sure, in all fields of um, science, interfaces are quite interesting because they can provide features which are not expected for any of the materials in contact itself, but at the interface, some new unique features can reveal themselves, which can be quite important and useful. So in our case, when we have interface between two materials, two mediums, so let us consider this model system as following. So we have one string which possesses some mu1 linear density, and this will be also correspond this will correspond to some velocity of the wave propagation v1. And then we have another string here which has mu2 and v2. So obviously, let's say they are made from the same material, but just one is thinner, another is thicker. So we can write that mu1 is smaller than mu2. We consider index 1 and 2 depending from where the incident wave is moving. So if we have some pulse which is moving towards the interface from medium 1, then this is our medium 1, then it moves to second medium with higher linear density, and this will be considered as medium 2. So what will happen at the interface. Any suggestions?
It will go faster.
What do you mean go faster? So you mean when, well, of course, velocity of the wave propagations will be different because they, as we described earlier, they depend on mu. So the larger density will result in smaller velocity. However, this single um, pulse will split in two pulses. So we will have so-called reflected pulse and transmitted pulse. Means one which is reflected from interface and comes back to the uh, medium from where incident came, and transmitted pulse which goes to another medium. So it will look, in this particular case, it will look like following. So here will be inverted pulse, which is transmitted, sorry, reflected. So that's our V1, and this is also V1, but in opposite direction. That's reflected. And here we will have a transmitted pulse, which moves in the same direction as the incident pulse, but with velocity v2, which corresponds to the properties of this medium. So now the question is, what do you think about amplitudes of these pulses? If we compare amplitude of incident pulse and amplitudes of transmitted and reflected pulses, they will be smaller. So why do you think they will be smaller? So we have a single pulse which carries some amount of energy and it's split it into two. Obviously, amplitudes cannot be larger of any transmitted or reflected pulses. They should be smaller than the amplitude of the incident ones. How they will be redistributed? Because obviously they will not be the same. Amplitude of reflected and transmitted pulses will not be the same. So we can calculate these amplitudes with the following equations. So reflected amplitude will be given as V2 minus V1 divided by V2 plus V1 times AI, which stands for the amplitude of the incident um, pulse or wave. So A transmitted, amplitude of the transmitted pulse, will be calculated as 2 times V2 divided by V2 plus V1 times AI. Keep in mind here it's important that we how we define medium 1 and medium 2. So in this case, medium 1 is from the left, which is the small linear density medium, and medium 2 is the high linear density medium, because we have incident pulse moving from left to right. So from first medium to second. If the direction is changing, if this pulse, initial pulse, is moving from right to left, then this will be medium 1 and this will be medium 2. So you need to be careful with defining these indexes. Another factor, well, I don't recall I mentioned or not, but you see here that the phase is changed. So when we have the reflection from the interface, when incident wave or pulse is moving from lower density medium to high density medium, the phase will always change to opposite. So we have pi phase change. However, that is not true if we have different direction of motion. So let us consider now another example. Let's assume that our incident pulse is moving from high density medium to low density medium. In this case, this will be medium 1, this will be medium 2. So how it will look after the pulse reaches the interface? So we have, this is our incident pulse, this is our reflected pulse, and this is our transmitted pulse. When the incident pulse is moving from high density medium towards the low density medium, there is no phase change for the reflected pulse or wave, and they remain in the same phase. For transmitted phase, doesn't matter from where and to where this pulse is moving, it will always be in the same phase as the incident pulse or wave. So that you don't worry about. But for reflection wave or pulse, you need to be careful and take into account the original medium where this pulse was formed. Is it denser or lighter than the medium towards which this pulse is moving? Because that will define the phase shift, and of course, if you don't take this into account, it will make cause some deviation from reality. So this is pretty much everything what I wanted to discuss today with you guys. And let us summarize. We first of all use our previously derived wave function to determine velocity and acceleration of y direction motion of elements of the string by taking first and second partial derivatives of wave function over time, assuming that x is constant. Then we derive equation for velocity of pulse or wave traveling along a string, where we have shown that the velocity will be proportional to the tension in the string as a driving force for this disturbance motion, and reversely proportional to the density of the linear density of the string. We introduced the concept of reflection and transmittance of waves, and it is necessary to keep in mind from which medium to which this initially generated pulse is moving, because if we have higher density and then we go, this pulse is moving to lower density medium, then we need to take into account the change of phase of reflected pulse by pi, so it goes to opposite orientation. And if initial medium is possesses less density, linear density, then this effect is not observed. We don't have any phase shift. So that is important. You keep this in mind. Obviously, amplitudes of transmitted and reflected waves are smaller than the amplitude of incident wave because we need to redistribute energy in two pulses instead of having it concentrated and confined in one pulse. Uh, and also we have an equation which, based on the ratio of the velocities of this pulse or wave in different mediums, V1 and V2, we can determine what will be the amplitude of the transmitted and reflected pulses or waves if we know the amplitude of the incident wave. Okay, we will consider discussion of waves, in particular transmittance, like let's say like transfer of energy with wave traveling along the string. So that will be topic of our discussion for Friday, how much energy per unit time can be transferred by such wave. And today, thank you very much for attention. See you next time. Have a good evening.